All right, this is not picking up at all. Huh. Hello. All right. Okay, great. So good morning, everyone. Welcome to CS 537. The microphone is working, so I am happy. All right, let's get started. So today we're going to be continuing our topic of memory virtualization. We just have one more lecture on this topic, and then we will be doing some review, and then we'll be switching over to concurrency. So what I think is great about this class is we have these very different three topics. So if you like one, you might like the next one. You might not. If you didn't like this topic, you very well might like the next one. So they're all very separate topics. But today we are talking about memory virtualization, specifically how to make our page tables smaller. All right, so begin with some announcements. You've all turned in Project 2. That's being currently graded. Project 3, that is available to you all. It is due 1 week from today exactly. So hopefully you all went to discussion section yesterday, and hopefully you learned a lot about fork and exec there, that it really is important to understand how fork works, how it makes a copy of the calling process, how that child process will be identical to the parent process except for that return code that's given to it. And then you can call exec on that child process, right? So this is a very fun project. It's really neat that you get to write your own shell, right? So you could use your own shell then whenever you want in your future life using Unix systems, but you probably won't. All right. Midterm 1. So that midterm is in exactly 2 weeks from today. So today's the last day to let me know if you have any conflicts, that you can't take the exam last night. If I haven't heard from you after today, you are taking that exam on that day. I have posted 2 sample exams with both. There's a version that just has the questions, and then there's a version that has questions and answers. I'm hearing more mumbling today, which is bugging me quite a bit. So if you could wait to talk until after class or until one of our many breaks. Thank you. All right, so there are 2 sample exams posted. I really recommend that you first look at the version that does not have the answers posted. Just do the version with just the questions, see if you get the right answers. Because there's something about looking at the version with the answers that it always seems like, yeah, I knew that. That was obvious. But if you really forced yourself to have to specify the answer, you would see that it was a little bit harder than you thought. So they are these very formulaic multiple choice exams. You'll see there's a lot of similarity between the 2 sample exams that are up there, so they are probably pretty good predictors for what your midterm will look like as well. So my plan is that next discussion section, the TAs will spend that discussion section going over one of those sample exams and doing more lecture content instead of talking about labs or projects. Yes? There will not be another project before the exam. Nope. I am slightly aware of your workload, yes. We're trying to give a little gap there, yeah. The mic is cutting in and out, as usual. Okay, and as usual, there are homeworks in Canvas. The next one that you're going to get is going to be a lot more interesting than I think all the previous ones, that it's going to be using paging with multiple levels of page tables like today's content. And I'll just get to that more later, but it's going to be harder than the previous ones. Okay, so today we're continuing to talk about how to virtualize memory. We're really looking at how we can make the page tables be pageable. How can we deal with the fact that page tables are huge, and how can we allocate page tables efficiently in memory? All right, so last lecture we were talking about TLBs, so let's review TLBs a little bit. Okay, but first I wanted to give more like big picture, make sure you understand who's managing the page tables. Obviously, it's the operating system that is creating these page tables. It is figuring out where a process's pages are allocated in physical memory. So it's up to the OS to fill in those values in the page table. You know, it figures out what that mapping is. It's the one that then fills in the values of the physical page numbers in the page table when it allocates memory to a process, or when it figures out where exactly that process will live in physical memory. So it's the OS that's setting up those page tables. All right. Okay. So then we were talking about how we do that address translation from virtual addresses to physical addresses. And there are basically 6 steps to this. The first step is if you have a virtual address, you need to pull out that VPN, the top order bits, to tell you what virtual page number you're looking at. Then you need to calculate from that where that is in the page table. So you remember the way that you do that is we're going to have a page table base register that points to the page table for this particular process. We know where that base is. This is an offset within that. And so we'll take that page table base register and we'll add the VPN times the size of an entry. So like 4 or 8 bytes. Those would be pretty typical sizes. So that'll give us an offset. This is just telling us now where the page table entry lives. You look in the page table entry, what will you see there? You'll see a physical page number or a physical frame number, plus some other bits that the OS cares about. We pull this out, and we use that to form our physical address with our physical page number, and then we use that same offset in our physical address, since the pages are the same size. All right. So the steps that were expensive here were anytime we have to read anything from memory. Since this page table is living in memory, that's expensive to do. We want to figure out how to make that faster. All right, so page tables are great, except for the fact that we have to do this extra memory reference and the fact that this page table is going to be huge. So with TLBs, we fixed the first problem where it was expensive to go to memory to read that page table entry. And so that's what we are showing in this animation here. You'll remember page tables live in physical memory, but we keep accessing the same page table entries over and over again when the user process accesses the same page over and over again. So for example, you have an array that's been allocated. You're likely to look at all of the offsets within a single page, so you keep accessing the same page. So the idea with a TLB is we are just going to cache some of those page translations in hardware, in a special TLB hardware cache, so that we don't have to go to main memory to get all of those page translations. All right. So to then elaborate on those 5 steps a little more, I hate this microphone. There is this step there now that after we've wow. Okay, well maybe that's good finally. Except you can hear every little breath. Yeah, the microphone's going crazy. It tells me it's at peak, it tells me it's at low, all these things in between. Okay, so after we get the VPN out of our virtual address, we use that to look up into our TLB. And if it is in there, that means we have a TLB hit, and it's directly telling us the PPN that we're looking for, so we don't have to go to the page table. But if we don't have a TLB hit, then we will go to the page table, do this exact same work as before. And then there'll be a TLB miss, and we'll have to load the contents of the TLB with that thing that we've just accessed. All right. So any questions about that? Okay. If I hold it like this, that's great. Okay. Yeah.
How do you stop the infinite loop? Like they want to get address of the page table. You still need to jump in that page.
So the address of the page table is in physical memory. So that's why there's no recursion there. Yeah. That we're told the direct base of that. Or it's an address. Yeah, it's a physical address. Yeah. All right. So even when I hold it like this, it's not working. Great. So who handles a TLB hit on that path? Is it the hardware or is it the operating system? So who does the work to figure out if this entry is in the TLB? And then gets to do most of the steps if it is a hit. So that's all done in hardware, right? That has to be done very quickly. If the virtual page number is in the TLB. The hardware did that lookup. It looked at all of the entries of the TLB in parallel, and it was able to extract the physical page number very quickly from that TLB, and then construct the physical address from that. So that's done in hardware. So then the question is, what happens if there's a TLB? See, it really... Okay. All right. So when there's a TLB miss, then the question is the hardware or the OS going to handle that? And so the answer is either one. Both answers are correct. There are some architectures that handle TLB misses in hardware and others that handle it in software, and there are advantages to both approaches. So what's the advantage to handling a TLB miss in hardware? Well, things are going to be faster, but then it means that you have to have a convention between hardware and software about exactly how that TLB is formatted. So to communicate between the OS and hardware, the convention is going to be that we're going to have this register that tells us where the base is of our page table. And then if there's a TLB miss, the hardware knows that's where the page table lives. The format of those page tables is a convention that can be followed. It says exactly which bits are being used for the PPN and which bits are being used for protection and other permission things. And so the hardware is able to walk those page table structures because it knows the exact format. It knows how to interpret every memory address there. Okay. I'm going to just give up on the microphone pretty soon. All right. Okay, so then the other approach, it heard me, and now it's penalizing me. So if the other approach is to have the operating system handle the TLB miss, the advantage of this is that we now can have any type of page table structures that we want. There's no agreement that has to occur between hardware and the operating system, and so we call this a software-managed TLB. And this gives us a lot of flexibility. You can really have any data structure you want. But of course, it still has to be the case that the OS runs, it figures out what the translation is between a physical page number and the physical page number with whatever data structures it wants, and then it loads that into the TLB. And so it has to be the OS that has the permissions to do that loading, that other processes couldn't just do that. All right. Since holding it didn't seem to matter, I would rather not have to hold the darn microphone. Okay. So to summarize then what we've learned about TLBs, we like having pages as our structure, but we don't want to have to access that page table on every memory access, so we're going to cache our recent page translations. That's going to be what's in this TLB. The TLB works really, really well on sequential workloads. So that's in a sequential workload, you tend to be accessing the same page over and over again in your user program. So therefore, it's the same page translations over and over again. And so the TLB is going to handle that really well. Workloads that have more temporal locality, those are only going to perform well if you have enough TLB entries, that by the time you get back to that same page translation, it needs to still be in the TLB, and it couldn't have been evicted by accessing other pages. All right, so we can have hardware or the operating system handling TLB misses. And then something we talked about in the last lecture was the fact that we have TLBs, it is increasing the cost of a context switch. So the cost of a context switch isn't just the cost of going into the OS, figuring out which process you want to run, modifying its registers, doing a trap return back into the next process. It also must take into account the cache state and the TLB state that's getting flushed when you switch between different processes. So when we switch between different processes, there's two different approaches we can use. One is to completely just get rid of all the entries in the TLB, invalidate everything in there so that you won't misinterpret the previous processes' page translations for your own. Or you can add these address space identifiers to every entry, and then you know which correspond to your mappings versus the others. Yeah? That's a great question, and it certainly seems like you could do that. So why don't we just save all of those translations And it certainly seems like something that would make a lot of sense to investigate. I don't know if anybody's done that or not. I mean, you would still have to do a little bit of extra work when you do the context switch to load it back up. That would be some memory accesses still that you need to do that. But that's a reasonable thing to try to see if that would improve. So you take a bit of a hit right away when you do your context switch. And with the current approach, it's more like a lazy evaluation, and so you would see slightly slower performance over the lifetime of your time slice as you start accessing that data. Whereas if you did your approach of loading it, it would take a little bit to get them all loaded, and you kind of want things running right away. But that seems like a neat thing to look into. Yep. So that is certainly the thing about systems. You can just come up with ideas like, wouldn't it make sense to do this? And then you can try it, and you can evaluate it and see if that type of thing actually improves performance. Great. All right, so we're talking about the fact that there are two disadvantages with paging. The first is what we've solved with TLBs. The second is that page tables are huge, and we need to decrease the amount of storage that's required for page tables. So let us now get into some new content. All right, so these are the types of simple formulas you were looking at in the past, but let's review and figure out how big the page tables are going to be for these four cases. And so the thing to remember again is this is what your virtual address looks like. I'm telling you how many bits for the total address. The page size is going to tell you how many bits you have for an offset. The number of pages is telling you how many bits you have for your VPN. And it's how many pages you have that tells you how big your page table is going to be. So please spend a couple of minutes and work through these with your neighbor and make sure that these are all straightforward computations for you. All right, so let's go over this. So I know this one's pretty straightforward, but we're going to be doing similar calculations that are going to get a little bit more involved with this. So make sure that you understand this first step. Okay, so if each page table entry is 2 bytes, and we're told that we have 32 virtual page numbers, that's how many entries we need to have. So it must be a total of 64 bytes, because this is a ridiculous architecture that we're assuming here. So this is a tiny page table, but it's just a ridiculous setup here. So that one's not very realistic. Page table size of 2 bytes. Each entry, page table entry size is 2 bytes. If our virtual address is 24, this whole thing is 24, and we have 16 pages, then how many bits do we have? We just have 16 pages. Did I write that? No, pages are 16 bytes, sorry. If pages are 16 bytes, then how many bits are being used in our offset? 4. Right, so we have 4 here, which must mean we have 20 bits for our VPN, which must mean that we have 2 to the 20 entries, and each entry is 2 bytes. So the total size will be 2 to the 21 bytes. Or that looks like 2 megabytes to me. Everybody agree? All right, so now every entry is 4 bytes. We have 32-bit virtual addresses. 32 bits for that whole thing. Pages are 4K. So if pages are 4K, how many bits must there be in the offset? 12. So how many bits are left for specifying a virtual page number? There's 20 bits left, so we have 2 to the 20 pages that we can address uniquely. So there's 2 to the 20 entries. Each entry is 4 bytes. So that'll be 2 to the 22 bytes for our page table. So now let's get into 64-bit addresses. 64 bits for the whole address. Each page is 4K, so it's the same number of bits that we must have in our offset to pick one of those bytes within 4K. How many pages do we now have? 52. So the size of this page table is 2 to the 52 times 4. So this is just a ridiculous gigabyte size page table. So clearly this is not what systems do. Systems do not have linear page tables that are megabytes or gigabytes in size. So we're going to have to do something smarter than our linear page tables that we've been looking at so far. All right. Okay. So why are page tables so large? So it's because we're using this ridiculous data structure where we're just assuming we have a linear page table. But basically, it's also how we use address spaces. So if you look at the view that a process has of its address space, what it sees in virtual memory, we are using a portion of the address space for its code. We are using the next portion for the heap. And then we are putting the stack at the other extreme of its address space and letting the two grow towards each other so that the heap and the stack would each be able to be the maximum amount. Right? So this let us make sure we could have as large as possible heap and stack when we don't know those sizes dynamically before the program starts. But the problem is we have all of these pages in our virtual address space. And I guess it's good that we don't have to allocate any physical memory for them, right? They're not allocated, they're not valid, they're not being used by the program. So we're not allocating any space for them in physical memory. The OS knows that, and it doesn't do that. So if you look at what the page table would look like for that previous program, you would see that the first couple of entries are valid, and then the last couple of entries are valid, pointing to whatever this user had in the stack. But we had to have invalid empty entries in our page table for all of that stuff we weren't using, just so that the address arithmetic would work correctly so that the process can access these pages down here. Right? So we still had to allocate these addresses in our page table even though they're all invalid. So we want to fix that and not use this type of data structure. So does that problem make sense to everybody? Okay. So what we're going to do is we're going to figure out how to avoid storing those entries. Okay. So there's going to be a couple of different approaches to how we can avoid having these linear page tables. Basically, we're going to have a range of different data structures instead of linear page tables. And so, of course, if we have our software-managed TLB, the OS can use whatever data structure it wants. There's no convention that we have to have with hardware. So you can be as clever as you want with this. So basically, remember that the hardware is looking for the VPN in the TLB on every memory access. That's always still the same process. That's the first step. And then if we have a TLB hit, we're done. We don't have to access these page tables. But if we have a miss, then we will trap into the OS, and the OS is going to do this work of looking up in its new data structures for this translation and loading the TLB. Okay? All right, so today we're going to look at a couple of different approaches. We'll look at segmented page tables, and then the big deal of the day, the multi-level page tables, and then wrap up with some inverted page tables. Okay. So one thing to notice is that our page table structures have contiguously allocated entries, right? There's a big bunch of dead space in the middle. And we saw this problem before for address spaces. So now we're seeing this problem with page tables. Before we saw this problem with address spaces. And having a bunch of invalid things in the middle of our data structure that has to be allocated contiguously, we solved in the past with segments, right? So what we're going to do now is we're going to have segments for each part of the page table, basically, so that we won't have to allocate these empty things here. We'll just say this part of the page table, for this segment, it starts here and it ends shortly thereafter. In this other segment, it starts here and it ends shortly thereafter. And so all of our addressing will be relative to the start of that portion of the page table. Okay. All right, so we're still going to use virtual addresses and split up the bits in order to figure out what segment we're addressing and then what page within that segment we're addressing. So it's still the case like before where we have segments. Those can be variable length. You'll have your code segment, your heap segment, your stack segment. That has a certain size. And then we're going to divide up each segment into pages. So we're going to get the best of both worlds here, where we can still take those pages and put them any place in physical memory. They're all exchangeable. We won't have any external fragmentation. We just have internal fragmentation. OK, so that's beautiful. And so we want to look at what our virtual address format is going to look like. What we're basically doing is we're taking that virtual address, and we're taking the top order bits and letting that specify a segment number. And now the remaining high order bits after that are specifying our virtual page number within that segment. And then we still have pages, so we still have an offset within that page. OK, so what we're going to now have is each segment's page tables will have a base, and it will have a bounds so that we make sure that we don't go past the end of that segment. So let's do some examples. All right. So each process, again, has its own segment table. This is different per process. But what does the segment table now contain? It contains the base, not of that where the user's process lives in physical memory. It's the base of the page table for this segment, right? And it tells me the bounds of that page table for that segment. And I'm kind of cheating here, and we'll just say bounds in this example. It's just like the number of PTE entries that are valid for that segment. I'm not doing any size or something like that. So it's just the number of entries that are valid. OK, so I'm telling you a nice format for addresses. We're using our classic 12 bits for an offset, which means 4K pages. How many bits do we have for a VPN? It's 8 bits. That's also an easy number to deal with since it's 2 hex digits. And then we have a segment number, which is 4 bits. And that's also easy because it's just 1 hex digit. So you can look at these addresses I've given you, and it's really easy to pull off which parts are for the segment and which parts are for the VPN and which are for the offset. OK, so when you look at this address here, you should be able to split this up. We have a 0 as the segment number. We have 02 as the VPN. And then we have 070 as our offset within that page. So what that means is, oops, you got to take, this is segment number 0. So I go into the segment table. I see that the base of its page table lives at this memory location, which is starting over here. And we need to look for page 2. That's what the second 2 hex digits are telling me. So this is the 0th, this is the first, this is the second page, page table entry. This is telling me the physical page number, right? That's what I got from doing that work. I found out the physical page number, just like before what was in page tables. It's telling me the physical page number for that page that I've been doing this translation. So therefore, it's physical page number 4. That's where I'm getting this physical page number 4 here. So our physical address. Physical memory doesn't have to have the same number of bits as virtual memory or your virtual address spaces, but they will always have the same number of bits for the offset. But you could have a different number of pages in the 2 spaces. But what we learned from this is that the physical page number is 4, and of course the offset remains 070. Okay. So the only way to figure out if you know this is for you to do it. So I will let you all spend a minute and do example 2, and then we'll make sure we all got that. So just do the next example. All right, so did you all get that? I hope. Let us look into why that is the right answer. So segment number is 2. So I use the segment table to find out where the base of the page table is for segment 2. It lives at physical memory address 001. That's where this page table lives in physical memory. And then we are told we need the second 012th entry in that page table. So it is 012. This is the physical page number where 202 lives. That's where that lives in physical memory. So we just take that page number and then concatenate that with the offset within that page. So that is how we're going to combine segmentation and paging. All right, what about the next one? Can you get this one quickly, or are you going to get tricked and spend more time than you need to figuring this one out? So one quick thing to always do is check if this thing is valid and what the permission bits are. So this poor user, they're trying to read from segment 1. They do not have read permission to that, so you don't have to do any more translations after that. They don't have permission. Segmentation fault. Okay. Next one, they're doing a write to segment 0. Can you discard this one quickly, or are you going to get sucked into a rat hole of doing address translations? Always check first. We're saying do a write to this one. You do not have write permission to segment 0. So another segmentation fault. OK, next time, segment 2, you're doing a write. You do have write permission. How long do you have to look at this one before you decide you shouldn't do a whole lot of work with it? So we are looking for page number 10 in hex. 10 in hex is larger than F, so we're going past our bounds. And I said just assume bounds is specified in terms of the number of entries. So 10 is past the bounds for that particular one. So that is not valid either. That segment is not that large. You're trying to access a page that's past the end of this segment. So therefore, error. And then this one is not going to be an error, so I will let you spend another minute figuring this one out. All right, so I hope this is what everybody got. Segment 2, it's all valid. The base of the page table for segment 2 lives at this physical address. We're looking for entry 3, 0123. It's 2A is the physical page number, where this page lives in physical memory. So I take 2A and concatenate with that the offset within that page. So 2A568. All right. Congratulations, everybody. Any questions about this? Yeah? Oh, great. So it's going to be per process, and it's not going to, I'm sure different people have done different things here, but you need this to be fast. This should be in registers. It's a small amount of information. There's a small number of segments that you have per process. So it should all be in registers as opposed to random memory. All right. Okay, so that's all in hardware. You'd obviously, when you do a context switch, you're going to need to change this segment table to be accurate for the current running process. Okay, so this is pretty good, combining segmentation and paging, but it's not going to fix all of our problems. So it is going to let us support these sparse address spaces, and by sparse address space, that means there's a lot of holes, there's a lot of free space in them, they're not compact, they're not contiguous. That we have sparse address spaces when we have a heap on one side and a stack on the other and all that dead space in between. So having segments is really great because now we don't have to allocate space for the page table entries that correspond to all of those addresses in the middle of our address space. And it lets us have all of the advantages of paging. We don't have any external fragmentation. We can just allocate any page we want. They're all equivalent. And as we'll see in our next lecture, this is going to let us run processes even when we don't have enough physical memory for all of the address spaces of all of the processes that want to run. We're able to swap out some of the pages to disk instead of having to be in physical memory. And then something I'll take a brief detour for is that it's going to allow us to have sharing at both the segment level and the paging level. So I wanted you to think for a minute, what does it mean for two processes to be sharing the same memory segment? We want it to be the case that that memory segment might even be mapped into different locations in each of their virtual address spaces, but they need to be accessing the same values for those variables, the same values in physical memory. So basically, we're going to map their address spaces to share the same physical pages at some point. So we can do this at both the segment level and the page level. So why was I showing this particular example? So the point here is you're going to see this is how you could set up a shared memory segment between two processes. So each of them will see the same physical memory, but they might have different addresses to get there. So in one process, P1, we're going to map the shared memory segment into segment 8, because I'm using the same format as always. That's telling us this is segment 8. And you'll notice that segment 8 for process 1, its page table starts at physical address 2. And whereas in 9, I've made that shared memory segment be mapped to segment 9 for it. And it's also pointing to the same base for that page table. So what that means is now when each of them does their accesses to page 2 within that segment, they're going to end up going to 0, 1, 2. They'll each see that that's at physical page 4. Right? Did I do that right? Yeah. So both of those virtual addresses in these different processes will actually be mapped to the same physical address. So when they do their loads and stores, they'll end up getting the same data that the other one sees there as well. So that's pretty neat how you can have processes share portions of their address space without having to share their whole address space. So that's pretty awesome. I don't have any animation there. The last one just shows, I wanted to show that you could also have sharing just at the page level. So in this example, we're looking at segment A. That has a certain base of 3, page 0 there. And just notice that that's also mapped to the same physical page as some other page in a different segment. So it is possible that you could have two processes with different virtual page numbers that end up mapping to the same physical page, and then they'd end up seeing the same data at that address. So you can have sharing at these other levels, but I think conceptually it makes the most sense to think of it as you have sharing of segments. It's a shared memory segment, and whatever you have there is also being shared with another process. All right. Okay. But this isn't solving every problem. So our problem is that we still have these really large page tables. We were looking at how large those page tables could be. They're just a problem. So if you really do have a large heap, if you really have allocated all the space on your heap, you still have to allocate all the space for that page table. Our previous approach of segmentation and paging, it was only really a win when we had a sparse address space and we weren't using a lot of it, and a lot of it was unallocated. If we really are using a lot of our heap, our page table is still going to be huge. So for example, if we have a 2-bit segment, 18 bits for the page number, 16 bits for the offset, and I tell you that each entry takes up 4 bytes, you can figure out how many pages we have, 2 to the 18, within this segment, that this segment has that many pages. It's still a 1 megabyte page table if we really are using up that whole heap. So we do not want to have a 1 megabyte page table and just allocate that in physical memory, because then we have to find 1 megabyte that's free, and it's hard to do that contiguously. So we want to page the page tables so that we chop this 1 megabyte up into 4 kilobyte chunks, and then those 4 kilobyte chunks can be placed wherever we want, just like every other page can. Okay? So we are going to get into how to do this. So our goal here is we're going to chop up page tables into page-sized units so that we don't have to allocate that whole page table contiguously. And so what this is going to mean is we're going to have a multi-level page table where the outer level points to the page table for the next level. And then we don't have to allocate page tables if we're not allocating the pages that need those translations. So that's pretty nice. And this is what is used in modern architectures, multi-level page tables. Again, this means if the hardware is interpreting this, that this is a convention, that the hardware knows exactly how we're structuring these page tables. Our address format is well-defined. Everybody knows how big the page is and what each of the different levels are. So I am going to give you a couple-minute break before you have to get into this one. All right. So maybe talk about traveling and vacation. What's the coolest, most awesome place you've ever been to? All right. Okay, everybody. Okay. So let us understand how we can page the page tables. So we're going to have this very stylized form for our format of our addresses. It's still going to be the case that the low order bits are picking an offset within our page. The high order bits are now specifying an outer page. What this really means is that this is pointing to another level of page tables. So for each process is going to have its own page directory. And that's just what we're calling the page tables for the page tables. So each process will know the base of its page directory, and then the outer bits are picking an entry within that. So if we have 8 bits for our outer page, it must be the case that we have 2 to the 8th entries in this top level directory. Then from this, we got the base of our next page table, and then this is the offset within that page table. So certainly other entries were pointing to other page tables, and those bits would have been picking offsets within other page tables. This inner page is picking the offset within the page table that we're pointing to, since we had those outer bits. And then at this point, we're going to be knowing what the final physical page number is, and we concatenate that again with the page offset. So at this point, we're getting the physical page number where that virtual page with all of those 18 bits has been allocated in physical memory. So examples, of course. Okay, so I'm making this a lot easier by only showing things that are valid. All right. So I will tell you where the page directory lives, and I will then tell you where certain page tables live that correspond to that. So this is physical page number 3. That's page tables. So if you ever get to here, then this is the page table that you'll look at. This is the page table that we get to that lives at physical page number 92 that we got to from over there. Okay, so what we need to do now is translate this virtual address. And I'm assuming 4 bits for the outer page, 4 bits for the inner page, 12 bits for the page offset. What are we going to do? So we look at the top 4 order bits, which is the first hex digit. It's 0, so it's the 0th entry in our page table. Set up very nicely. You can tell you're not making mistakes here. The page table for the outer page 0 lives at physical page 3 in physical memory. I've told you with the second column, second table, what its contents are. And now we're told you need to look at the first page within that page table. So that will give us the physical page number of 23. Double check that it's valid. It looks good. So we'll translate 0, 1 into 2, 3. See if that's what I have here. It is indeed same offset within that page. And so again, notice that if we have invalid entries in our page directory, that means we don't even need to allocate the page tables that correspond to all of those entries. Those pages aren't valid. We don't even need to have page tables for them. So that's where we're doing this big savings. And the other really nice thing is that we're going to construct this portion of the page table to exactly fit within a page so that we can move them around interchangeably. Okay, so let me give you another example for you to get to do. 2 address translations. Have a go at it, and we will reconvene. All right. So this example was set up to lead you to the right answers, right? So the outer bits will tell us which outer page table we need to be looking at from the page directory. So there's only one page directory in this example, but really every process has its own page directory. We would need to know where the base is for the currently running one. But we are looking for the 0th entry, so we get that its page table lives in physical page number 3. I told you that that's what's here. We're going to get the 4th entry, 0, 1, 2, 3, 4. 04 virtual page number corresponds to physical page number 80. So then we just concatenate our offset there. So it should be physical page 80 with that offset. Any questions about that? So then the next one, again, set up nicely. We're looking at outer page F. That is the only one that's shown there. The page table for that outer page lives at physical address 92, or the one that corresponds to physical page 92. That's the only one I'm showing you here. You need to get the ETH entry from that. If you count all of that, that should be the ETH entry. And so that lives at physical page 55ED0. Any questions about that? Yes? Well, I meant to count correctly. So on this outer one or this one? So it should be, if I could see my highlighter, it would be easier. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, imagine there's some zeros in there. Yeah, I didn't mean to let's trick you here. All right. I only see 14 now. All right, so other than that, any other things people see or don't understand? Okay. So this example was set up to be really straightforward. I'm going to have a lovely homework for you all to do that will actually stress your abilities, I assure you. So this example, it's not available yet. It should be in a couple of days or today. So you're going to be doing multi-level page translations, but the bits are not going to be so nice. So it's going to be the case that, I think pages are 10 bits. So that means you can't just look at the hex digits to see exactly what virtual page number you're looking at. You have to write out the bits and transform them and see really how many bits are going to the page number versus the offset. So that's one complication. The other complication is it's just going to show a dump of physical memory with no hints about which ones seem to be page tables or which ones are really valid. And so if you start going down the wrong path, you will just happily keep going down the wrong path because we filled in everything for you. So this will really, really stress that you understand how to do these translations with 2 levels. So it's just 2 levels, at least, in that homework. But you'll see more of that when you do that homework. Okay. Now it turns out real systems do not just have 2 levels of page tables. So as your address space gets larger, we're going to run into the problem where maybe that inner level page table isn't fitting in a page anymore. So the key is we need to make it so that each page table will fit within a page. So how are we going to do that? So it really depends upon what your address structure looks like. So let's assume we have a 30-bit address, 12-bit page offsets, or 4 kilobyte pages. How should we structure this so that the page tables that we're indexing with these bits, the inner page bits, that page table will fit within a page? So there's some calculations we can do to figure out how many bits should be devoted to the inner page, assuming a 4 kilobyte page. So again, our goal is that each of those inner page tables has to fit within a page. They have to fill up 4 kilobytes. If I tell you how big each of those page table entries is, then you can figure out how many page table entries there must be. So we'll do our usual, assume that each page table entry takes up 4 bytes. And then if each page is 4 kilobytes, and each of them entries is taking up 4 bytes, it must mean that we can have 1,000 entries on that inner page table, right? 1,000 times 4 is 4K. So that's how many entries we can fit here. And so what does that tell us about our address format? If this is picking 1,000 entries, then it must mean that we have 10 bits there, right? Since 2 to the 10 is 1,024. So in our address format, we will devote 10 bits to the inner page. And then since I told you how large the whole address is, you can figure out how many bits are obviously in the outer page. So 30 minus 10 and 12 gives us 8 bits. So this would be a reasonable address format if you had a 30-bit address. So does the motivation for that make sense to everybody, that we need to make those inner page tables fit within a page? Okay. Now, the problem is we don't have 30-bit addresses these days. We might have a machine with 64-bit addresses. So what are you going to do there? We are not just going to have 2 levels of page tables. We will probably have 3 levels. So let's assume we have our 64-bit address. We are going to end up recursively applying that math to multiple levels of page tables. And so let's just first figure out how large of a virtual how large of a virtual address space we can support, assuming 4 kilobyte pages and 4 byte entries. So if we only had 1 level page table, then that would mean that we could only fit 1,000 entries there, 1,000 pages. Yeah. So we can fit basically 1,000 entries on every level. So here, how large is our address space? We could have 1,000 pages. Each of them is 4. So we could have a 4 megabyte address space with just one level. As you add on more levels, that lets us have more page tables that we are able to go through. So we are able to get basically in this tree, this hierarchy of page tables, you get 1,000 more for every one that you had in the past. So with 3 levels, you're going to be able to support this size of address space, 4 terabytes. That's plenty for what we can imagine doing these days. And so a 3-level page table certainly maps what users are going to expect these days. Whereas a 4 gigabyte address space, maybe you have an application that wants more than that. So we are going to need 3 levels of page tables. Because you really would not be able to support a user process that wanted to have a larger address space than 4 gigabytes if you only have 2 levels of page tables. OK, so I was really assuming there was going to be some more math in here. Maybe that's after this. Maybe I'll remove that slide. OK. So I would have liked to have done a calculation where we figure out how many bits we're going to use for each level, but I seem to have removed that. So anyways, so I want to remind you that we are using TLBs with these multiple levels of page tables. So we're first going to go to the TLB, and if our virtual page number, which is all of those inner and outer bits for all of those different levels, that's what we're still using for our tag into the TLB. So if that's in there, we get to shortcut doing all of these lookups through all of the page tables. Because as we add more page tables, that's just more memory references, right? With a 2-level page table, that means 2 extra memory references just to do what the user wanted, just to do 1 page translation. OK. So again, TLBs become more and more useful the more levels of page tables we have. So here, let's assume we have a 3-level page table. Let's assume we have these tiny pages for our example, because we're only going to have a 16-bit address. And then let's assume that the currently running process has an address space identifier of 211. So let us figure out how many physical accesses to memory are you actually going to need to do for each instruction. And we'll assume that the TLB doesn't change contents as we go. We have enough space. We can just, we'll have more entries there. So this instruction, for example, we need to fetch it. It lives at virtual address AA10. And that instruction is trying to do a move or a load from that memory address of 1111 into a register. So we want to do some of the lookups to see, do these pages seem to live, are there translations in the TLB right now? So it's useful to look at what our format is for our addresses. So I said this one's set up to be nice. If we have 256-byte pages, that's 2 to the 8th, right? So this is 8 bits. So this is going to be 2 hex digits for our page offset. I told you the total thing is 16. And what other stuff did I tell you? 3-level page table. Well, that doesn't really matter for this example, because what matters is that it's telling us that our virtual page number is the other 8 bits. And that is what we're looking for in the TLB, right? It doesn't matter how that's being split across outer, inner, whatever page tables. This is the tag that we're looking for in the TLB. OK. So when we take the address AA10, the 10 is the offset. AA is the virtual page number. And so is AA in the TLB? No, it is not. So we're going to have a TLB miss. Whenever we have a TLB miss, that means we have to do a bunch of lookups. we have to go into that, we have to do one address translation for every level. Remember when we did one level linear page tables, that meant we were incurring one extra lookup. When we have two levels, it's going to be two memory lookups. When we have three levels, it's three memory accesses just to do that page translation from AA to whatever it is. We don't know what it is in this example. So we have to do three address translations, memory lookups, because we had a TLB miss. And then the user, we get to do what they really wanted to do, which was fetch the instruction at whatever physical address that is, that now we know what it is. So that's going to incur 4 memory accesses just to do that one little instruction. That's how important TLBs are. We better be hitting in the TLB all the time, because this is really, really expensive if we don't. OK, and then we need to do the actual instruction, which is to do a load from page 1.1. Do we have that in the TLB? Doesn't look like it. We're not doing very well yet. We'll have a TLB miss. That's going to be 3 address translations again, since it's a 3-level page table. And then we're going to do the memory instruction itself, which is another memory access. So that's 8 memory accesses in that tiny little assembly instruction there. OK, so that one was horrible. Now we are fetching another instruction that lives at BB13. So is this in our TLB? So we look for BB. It is this address space identifier. That's great. It is valid. And so now I don't care what's in those multi-levels of page tables. I just know the answer. That virtual page lives at physical page 91. I am very, very happy. So now I can just fetch the instruction that lives at 91.13. I find out that it's an add, and then I can do that add. So this instruction that hit in the TLB, it only involves one memory access, which was to do the actual instruction fetch from the physical address that we were able to figure out. So does that make sense to everybody with the hit? OK. All right, and I skipped this step before in A here, where we had a miss. We would, of course, have loaded the TLB with the new information that we got to help us out in the future. OK, next memory fetch is to virtual page 5. Is that here? Something funny is looking on. So the ACID of 122 is not us. We better not use that one. Here's us, but this entry is not valid in the TLB. Maybe it was from a previous time we were, who knows why. It's not valid, though, so we cannot use it. This is a TLB miss. We have to do the page walk involving 3 memory accesses, and then we're able to fetch the instruction that we wanted. Now we do this move instruction. That's a store into FF10. Is FF in the TLB? It is. It's valid. So we know that we're going to be doing a move into physical address. Is this right? 05 is 91. Yep. And then I'm suspicious. Sorry. FF. Great, great, great. This is what we were looking at. FF is physical page 23. The offset was 10. Offset is 10. All right, so that is how we will use a TLB to short circuit a lot of these page lookups and to translate virtual page numbers to physical page numbers. Any questions about using the TLB for this example? All right, so it's just a lot of grungy looking at addresses for a while. All right, finally, something different. OK, inverted page tables. So this is a new concept. So the observation here is that we really don't need to know the address translation for pages in our virtual address space that aren't valid. So why are we kind of doing a data structure that's focused around virtual addresses? So what some architectures have tried to do is you have an inverted page table. By inverted, it means you're using the physical page number to figure out things about the virtual address number. Now, we always have to do our lookups, though we have a virtual address and we need to get to a physical address. But we're keeping our data structure somehow proportional to the number of physical pages that we have instead. So you could imagine just having like some list structure where you have our tree. You have one entry for every physical page. You search through your list or you search through that tree, and you try to find the virtual page number that you're looking for. Now that's clearly ridiculously slow. You can't be searching through a data structure every time you need to do an address translation. That's not going to work. So what systems have done then is to use our fine technique of hashing. So basically, you just take a hash over your virtual page number and your address space identifier. That gets you to a small portion of your data set. Then you can look very quickly to see if anything that hashed to that same value actually has your correct VPN and address space identifier, and it will tell you in that data structure where the physical frame number is that you're looking for. So it's just kind of like a hash table to help you get to the translation of virtual page number to physical page number. And you only have to have as many entries as you had physical pages. So if you can't find the translation in the structure, that means that it's not a valid translation. Yeah? Well, I think they make the structure to start with proportional to the amount of physical memory that they have, so that everything is just proportional to the amount of physical memory, since that's not going to change over time. And so sure, at first, it's going to be very sparse. You won't have too many virtual addresses that you're translating. And then it's going to fill up over time, but it shouldn't be the case that your virtual address space is a lot larger than physical memory. But this is more done like in research systems where they're like building something interesting. They want to stress some different part of the system, and it's not going to support swapping and paging to disk as well as what we'll talk about in our next lecture. All right. Okay. So, but just still remember, even when you have an inverted page table or you have other interesting data structures, we still always have that TLB that's happening before this, that it's only if we have a TLB miss that we go through these other data structures that we might be keeping. Okay, so today we've been talking about how to have better page table structures, that the goal is to keep each of the page tables fitting within a page. And in order to do that, you really do need to look at the format of your virtual addresses to make sure that you're using the right number of bits to access into each. And then now we'll have this page level directory at the start of it that's unique to every process that tells you where all of the page tables live for that process. Okay, so next lecture we're going to talk about what we're going to do when we don't have enough physical memory for all of the processes that are running. We're going to move up a little bit. I don't think we're going to obsess so much about bits ever again in this course. I think that was the most hexadecimal arithmetic we will be doing. Okay, so it's a little bit higher level in our next lecture.